All right, probably without knowing it, without realizing it, all of the areas you did last night, or whenever you did your homework, passed the VLT. You probably didn't think about that consciously, but they all did. Okay, so if a region passes the VLT, in other words, a vertical line doesn't intersect the same function twice. And then what you did was you stayed in terms of x. Everything you did was dx. And you worked working across the x-axis. Left to right. All right, so today we need to look at, well, what do we do if a region does not pass the vertical line test? So that's day 2. And so in a similar way, if a region fails, and I'll draw a picture of one that fails so you can see what I'm talking about. So if a region fails the VLT, then we switch into y terms, and we work along the y-axis. Bottom to top, or low to high. Okay, so let me show you a classic example of something that would fail the vertical line test. Any function that would fail. All right, let's consider the graph of a sideways parabola. Okay, that sideways parabola clearly fails the vertical line test. Okay, we're going to call that g of y. So we express that in terms of y. Now, any function that's expressed in terms of y means it starts with x equals something. Just like a function that would be expressed in terms of x starts with y equals blah, 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 blah. Now, our calculators are built to handle functions that are in y terms. So we have a y equals button. So we're going to have to think a little bit differently when we want to do x equals and have it be in terms of y. Okay, so this function fails the VLT. As soon as you recognize that, you think, okay, if I'm going to find the area, I'm going to need to be thinking in terms of y instead. All right, and so then let's suppose that we cut that with a linear function. And we'll call that one f of y. Its intersection points will still be x1, y1, and the other one up here would be x2, y2. In order to find the area bounded in between the region of these two boundaries, we set up an integral that's going to be evaluated in terms of y. And so our area will look like this. The integral will go on the values of y from the smaller, the lower, to the upper. And so that would be y1 to y2. So those are the values of the y coordinates of the intersection point. Okay, now we need a subtraction. But the question is always which one comes first. Okay. Well, as you're determining which one comes first, you're going to do the reverse of what you did before, and we're going to, instead of going left to right, we're going to go right to left. And so we think about an arrow. Yesterday we talked about an arrow. We think about an arrow that comes and it wants to pierce the region from right to left instead of from left to right. And the first equation it will pierce or encounter would be the linear one, and so that would be the one that you would list first. And so that would be f of y minus, and then the other one, which would it encounter second, so then g of y, the whole thing dy to show that we're moving along the y-axis from for y terms. Now, if you happen to get them backwards, you'll get an answer that is negative. So that's a quick fix, or at least something to look at, first of all, to make sure that, assuming you didn't make any other computational errors, you would make sure that you either have your bounds correct and have the order of your subtraction correct. So let's do an actual problem that's got functions and numbers and stuff. Analytically determine or analytically evaluate. As soon as you see the word analytically, it implies that there's no calculator involved. All right, analytically evaluate the area between x equals negative y squared. So it's kind of a dead giveaway right there when the function is formatted x equals. It's probably going to fail the vertical line test. And x equals negative 2 minus y. Use Math 9 to verify. So I'm going to teach you, first we'll do it by hand, then I'm going to teach you your calculator, even though all it has is a y equals button, it is still able to handle things that are in terms of y, and I'll just show you how it works. All right, so we need to have a picture so that we can find out where the intersection points are, and we need to figure out, moving now from right to left, which one we would encounter first. So x equals negative y squared is a parabola again, but because of the negative, it's been reflected backwards. And so this parabola looks like this. Okay, and that is the equation x equals negative y squared. All right, it fails the VLT. The line x equals negative 2 minus y. For me, I'm not super good at graphing those unless I convert it into y equals mx plus b and get an idea of what it looks like graphing. Oh, by the way, the origin is right here, okay, in case you're looking for a reference point. So I would take that and I would get y by itself. And I would solve for y there. And so it's going to be y equals negative x minus 2. So that just helps me, I can graph that better. Oh, it has a negative slope, and it's going through negative 2 on the x-axis, on the y-axis. And so my graph, if this is where 0, 0 is, then negative 2 is going to be about down here. And it's going to have a slope of negative 1. So my linear piece will be coming through that way. And that's the equation x equals negative 2 minus y. Now we want to find the intersection points. And so to find those intersection points, we set these two equations equal to each other. So we'll take the parabola, negative y squared, and set it equal to negative 2 minus y. So algebraically, it shouldn't be a problem to solve these. Let's get rid of all the negatives by dividing through by negative 1. And then setting this equation equal to 0. So I'll have y squared plus y minus 2 equals 0, which factored gives me y plus 2 and y minus 1, which means the values for y are negative 2 and positive 1. These are now the y coordinates of the intersection point. So my intersection points are here and here. something, comma, -2. Yeah. What did I do? Oh, I forgot to change. I didn't change the sign. Thank you. Okay, thank you. I didn't change it here. Good. So we'll fix that. Okay. Minus y, so -2 plus 1. So 2 and -1. There we go. That looks a lot better. Okay. All right. So the lower one is actually in the -1 value, and the upper one is something, comma, 2. Now you don't even have to find the x values, because I don't need them. I only need the y values to be able to integrate from the lower to the higher. All right, so now I'm ready to set up my integral to find the area of that value. So my integral will go from the lower y coordinate, which was -1, to the upper y coordinate, which is 2. And then in terms of setting up the order, you go right to left. And so we'll look at this equation and we'll imagine if we're coming from the right and we're intersecting this and we're trying to pierce it with an arrow, we would encounter these parabola first, the sideways parabola. So we'll have -y² minus the linear piece, which is -2 minus y. So I'll be able to clean that up, and then I say dy. So now we're ready to do this by hand. So -1 to 2, -y² plus 2 plus y dy. So I distribute my negative and make sure my signs are cleaned up. So my integral yields the antiderivative of -1/3 y cubed plus 2y plus 1/2 y² plus c going from -1 to 2. Now there's no symmetry I can use to my advantage here because the region was not symmetric, so I'm going to have to plug both of these in. So -1/3 times 8 plus 2 times 2 plus 1/2 times 4 minus 1/3 times -1 minus 2 times -1 minus 1/2 times +1. And my plus c and my minus c canceled each other out. So -8/3 plus 4 plus 2 minus 1/3 plus 2 minus 1/2. So my thirds, I always look for like terms in terms of fractions. So -8/3 and -1/3, those combine together very nicely for me to give me -3, -9/3. And then plus 8, that would be the 4 plus 2 plus 2, and the -1/2. So altogether, I have 4.5 square units of area bounded between those two functions. Okay, so any questions on the analytical part of it? Okay, then let me show you how to do that on your calculator. So if you don't have that out already, would you get that out?